We've seen the conic sections defined using a focus or multiple foci and directrix for a parabola. And we can actually define all the conics using a focus and a directrix. Here's the definition. We're going to let F, the focus, be a fixed point, and D, a fixed line in a plane. The set of all points such that the distance from the point to the focus divided by the distance from the point to the directrix equals some constant number, okay, will define a conic. This constant number, E, if it's 1, then this gives a parabola. If that number is between 0 and 1, it gives an ellipse, and if that number is greater than 1, it gives a hyperbola. Here we have a picture of an example with an ellipse, of course. We've got here a focus, and we've got a directrix. And what we're saying is this distance here from that focus to any point, and the distance from that point to the directrix, okay, these two distances, if you divide them, the distance from the point to the focus over the distance from the point to the directrix, you'll always get the same number, okay? So that ratio is what is constant. And it turns out that this definition of conics actually makes it so that describing the equation of a conic in the polar coordinate system is very easy. These are the polar equations of conics. So, first of all, in the polar system, the pole is going to be a focus of a conic. We've got the eccentricity E, that constant ratio, and then a directrix that is d units from the focus. These are the four possible forms of the polar equation of a conic. You'll note that they all have the same ED in the numerator. They all have a 1 in the denominator, and then either a plus or minus E times either a sine or a cosine function. And if it's a cosine, then we know that the directrix will be vertical, which means that the conic will look like it has a horizontal orientation. And if it's a sine, that means the directrix will be horizontal and the conic will look vertical in orientation. And then finally, whether it's a plus or a minus determines the placement of the directrix relative to the actual conic. So if it's a plus, then the directrix is larger, so to the right or above the pole. And if it's a negative, then the directrix is to the left or below the pole. So these are the equations of conics, and remember that E determines what type of conic it is, right? If E is between 0 and 1, it's an ellipse. If E equals 1, it's a parabola, and if E is greater than 1, it is a hyperbola. So let's go ahead and derive just one of these forms here. So we have our pole here at the point at the pole. The focus at the pole, and this distance right here, divided by the distance from the point to the directrix, that ratio is always going to be the same. So here's what we're going to do. We're going to go ahead and just write that. So this is the point F. This is the point P. And of course, this is the directrix D. Now this point P, if we're in polar coordinates, we know can be represented with r, theta. Okay, with of course the polar axis being this axis here. And this angle here is theta. Now to get the equation, one of these equations of the conics, we're going to look at that distance. The distance from the point P to the focus F divided by the distance from the point P to the directrix is always a constant. It's this number E. Now we're going to actually take this and we're going to multiply both sides by this denominator here. So we get the distance from the point P to F equal to E times the distance from the point P to the directrix D. Well, now, if we look at the distance from point P to F, we know that that is r, because this point is r theta. We know that r is the distance from the focus, from a pole to a point. And so that distance, P to F, this is r. So I'll write that here, r equals, and then we have E times, and now this distance from P to D we need to get. If we look at this point that's directly above the focus, we know that this distance right here, we're going to call that D. Okay, the distance from the focus to the directrix is D. That's what we set up here. We're going to call that D units from the focus. Okay, and this distance right here, we can actually see that this is part of a triangle. If I'm going to go ahead and just drop that down right there, this angle is theta. And so then we know that this length right here, cosine of theta, is that length over r. In other words, this length here is r times the cosine of theta. And so here I have E times, and then this distance from P to the directrix is the sum of those two things, D plus r cosine of theta. Okay, so now if I go ahead and distribute this E, I get r equals ED plus ER cosine of theta. Now I'm going to isolate r, so I'm going to move this term here to the left, and I get r minus ER cosine of theta equals ED. Now factoring the r out, I get r times 1 minus E times cosine of theta equals ED. And now we can divide by this 1 minus E cosine theta to get r. So we get r equals E times D over 1 minus E cosine of theta. You can see that that is the equation. The way that I've drawn this here, I've got a vertical directrix that is to the left of the focus, and that is precisely this right here, vertical directrix to the left of the focus, which is the pole. Okay, and that's our equation. So the other three are derived similarly, drawing a picture just like this, but placing the directrix on either side, or vertically or horizontally.